Okay, here we're going to do a little screencast on the note of history of atomic theory. Up to this point, we've talked about the elements, we've talked about the grouping of the elements, we've talked about the properties of some of these elements. But what we want to do now is we want to go back and not necessarily look at the periodic table in terms of each element and their properties, but we want to look at just atoms themselves and how the idea of the atom has come about and what our current idea of atoms are, so that we can make sense of those properties. If we understand what makes up an atom, we can then start to theoretically explain these properties of the atoms. Okay, so let's talk about our first interesting subject here, and his name is Democritus, a Greek philosopher. There are many Greek philosophers that you probably have heard of. Democritus is important, really, in this discussion for one reason. All right, he believed that all substances are made up of small indivisible particles, and what that means is that he believed that if you were to take a piece of matter, such as an apple, and you were to take a knife and cut it in half and cut that half in half and keep cutting, you would eventually get to the smallest piece of what that apple could be made up of, and you couldn't cut it any further. That the universe was made up of tiny little pieces stuck together that you couldn't break down. And he used the Greek term atomos, that means indivisible, to describe these little pieces of matter. And the real reason that we're talking about him here is because he used this term atomos, and that's where our term, the atom, comes from, right? And we know that an atom is the smallest part of an element that has the properties of that element. And in a moment, you'll be able to write this stuff down when you go over the notes. I just want to talk a little bit more about some Greek philosophers, so let's just head to the internet here. Let's take a look at Democritus. Democritus, all right, beautiful. And so here we've got some pictures of Democritus, not a big deal. But you'll notice down here other searches, and we've got another famous philosopher down here named Aristotle. All right, and if we take a look, Democritus, born 1460, died, oh my goodness, yeah, died 370 BC. Take a look at Aristotle here. Aristotle is born just when Democritus is kind of ending his career. But Aristotle is important in this discussion because Aristotle had an opposing view of Democritus's theory. Aristotle believed that if you had a piece of apple and you cut it in half and cut it in half again, that you could continually cut forever, all right, and that there would never be a smallest piece. The term we use to describe a type of material that doesn't really have a distinct structure is amorphous. It's kind of like Play-Doh. We would say Play-Doh is amorphous, all right, and we would say that a bag of popcorn is discrete. It's made up of little tiny pieces, all right. So Democritus believed that the universe was discrete, and Aristotle believed that the universe was amorphous. The problem with Aristotle is that he was very widely accepted in terms of his theories and his ideas, and therefore when scientists, theorists, Greek philosophers that kind of evolved into scientists as we went through the ages, believed everything Aristotle said and never questioned kind of his ideas, and that kind of let science kind of sit in this time period of non-change because they just blindly believed Aristotle's theory, and no one really questioned it. And so therefore there's a long period of time that science kind of didn't advance. All right. Some other interesting people here. We're going to get to John Dalton in a moment. Empedocles. Empedocles is another interesting fella in the story of chemistry. Uh, you've probably heard of the ancient four elements of the Greeks, and it was Empedocles that kind of came up with this idea, the theory of the four classic elements. All right, here we've got an interesting image here. Maybe if it comes up for me. So here we've got our four, elements: earth, air, fire, water. All right, and so Empedocles kind of originated this idea of the elements, not atoms, but the elements themselves. And that's again a very important starting point to chemistry itself. This idea that there were certain fundamental things. We now know there are many other elements, and they're not just made up of those things, right? Obviously, fire is not an element. But again, Empedocles is kind of an interesting guy. Many of these guys in here are very interesting in terms of the history of science. Lucretius, oh, I can't remember what he did. Anyway, lots of them. Let's keep going then on the note. Okay, so Democritus's big addition to this is the term atomos. Again, like I said, everybody believed Aristotle, and so then things kind of stagnated. And then we jump ahead, and we notice we're now at the early 1800s, so we've jumped ahead like 2,000 years to even more. There is an interesting guy that we need to talk a little bit about before Dalton. So we'll go back to the internet here, and we'll do a little check for a guy by the name of what's going on here? Lavoisier. Lavoisier, okay, so there's Antoine Lavoisier. All right, and again, he's again a very important player in the world of chemistry, and we'll be hearing about him, and I probably have already mentioned him. And again, he's very important in that he kind of organized chemistry, started to get people to talk about naming them in a very systematic way. All right. And he's existing in a time just before Dalton. All right, so here we've got John Dalton, again, another important thing. Again, Lavoisier didn't necessarily have an idea of what the atom was, but he was just trying to organize the chemical world by giving them fundamental names and having people do experiments in a very rigorous way. And again, advanced things greatly in terms of the study of gases and the study of the way things react and the way things behave. He actually came up with a very important law that we now know exists in all chemical reactions. It's called the law of conservation of mass. And it states that if you have a chemical reaction, all of the mass that you had at the beginning of the reaction in your reactants would be the same as the mass that you have in your products at the end. And that's a very important thing, something I needed to just mention before we talked about Dalton. So a few years after Lavoisier, here we've got Dalton, like I said, early 1800s. Now, John Dalton wasn't really out to kind of describe matter in terms of atoms. What he was trying to study was essentially the way gases can dissolve in liquids. And the easiest way he could explain that was to imagine that the gases were made up of tiny little particles. You can think of it kind of like sand, little grains of sand, and that the liquid was made up of, again, different types of tiny little particles. You could think of that as maybe gravel, like large stones. And you could then imagine that if you poured the sand on the gravel, that then the little pieces of sand could fit into the gravel, and that would be like dissolving. That would be like a gas going into a liquid and kind of dissolving. So he was attempting to describe a property of gases and how they dissolve in liquids. It turns out that he was right, that matter is made up of these tiny little particles, and in the end he realized that was a more important way of talking about things. So he came up with five main postulates or rules, and you'll write these down in a moment when you go through the note. All matter is comprised of tiny indivisible particles called atoms. He used the term atoms because he knew his history and he knew about Democritus and his term atomos. And And so he used that term atom to describe these little particles. And, the rest is history, right? We now talk about atoms all the time in chemistry. Okay, so all matter is comprised of tiny indivisible particles called atoms. All atoms of a particular element have identical properties. And we already know that, right? But that was kind of groundbreaking, back in the 1800s. So it meant that atoms of one particular element are the same as all of the other atoms of that same element. In other words, they're identical. They don't differ. All atoms of different elements have different properties. And again, that makes sense to us, but back then it was important to be stated. So an atom of hydrogen was much different than an atom of oxygen, all right? And they had different properties. That's what made them different. Other postulates, atoms can combine in constant ratios to form groups of atoms called molecules. Now, Dalton did not come up with the term molecule himself. I believe he used a term like compound atoms, right? Things that contain more than one atom. The term molecule came along a little later on. I cannot remember who originated the term, but it's not important here. And during a chemical reaction, atoms join together or separate from each other and are not destroyed. So this is groundbreaking. This is the most important part of his atomic theory, that during a reaction, atoms simply just kind of trade places and move around and form new partnerships to form new molecules, but they are not destroyed. And that's the important part that goes along with Lavoisier's idea. All right? Okay. So we call Dalton's atom the billiard ball atom because he really didn't have any features in it. There's no electrons or no protons. It's just a sphere, just a thing. So it's like a pool ball, right? It doesn't have any features to it. So that's why we call it the billiard ball atom. All right. So what made this so great? Well, I've already talked about the law of conservation of mass in terms of Lavoisier. That was what he theorized from his experiments, that's what he observed in his experiments, and this kind of supported it. So his atomic theory supported the law of conservation of mass. In any physical or chemical change, the total mass of the system stays the same. That's one way of stating it. Another way of stating it is the total mass of the reactants equals the total mass of the product. And a third way of stating it, matter is neither. And if I were here, I would ask people to give me your input on how to complete the fill in the blanks. But it is created, pardon the scribbling, I haven't used this in a while, or destroyed. All right? So matter is neither created or destroyed. All right? It means that it just kind of rearranges and trade takes places. Okay. The other important law that was supported is the law of constant composition. Chemists realized that a compound made up of more than one type of atom was always the same. It didn't matter where you got that particular compound. So if somebody took some water out of the Thames River in London, England, and analyzed it, they would find that it was 11% hydrogen and 89% oxygen. And if they took some water from, say, the Sydenham River in mighty Albinston, Ontario, and they analyzed it, they would also find that it was 11% hydrogen and 89% oxygen. And, to scientists a long time ago, that was surprising to them, and once they started to analyze water in different places, they realized that, all water is made up of 11% hydrogen and 89% oxygen. And if we think of atoms if we think of molecules as being made up of certain groupings of atoms, which we now know to be, right, something like this, H2O, and we know this now, but they didn't know that back then it makes good sense that our, mass of the hydrogen, 11%, mass of the oxygen, 89%, is, it's always going to be the same because all water is made up of the same particles. So the law of constant composition was another very important idea that was kind of confirmed by this theory. Okay, that's some videos there. Oh, I don't want to play the videos. Let's advance. Okay, let's jump ahead now to a guy by the name of Thomson. So we've jumped ahead about 100 years, and that's not very long ago from now. So that's like about 110 years ago, this type of idea. Thomson was taking some ideas from a guy by the name of, well, let's take a look here. Oh, let's shut that off, and let's look at Crookes tube, a Crookes tube. All right, Crookes tube. Click on that. So here we've got some images for some Crookes tubes. This is an interesting thing. So here we got a whole bunch of them. Let's take a look at these. A scientist by the name of Crookes was working with electricity. All right, with the advance of electricity in the 1800s, chemists had a new tool that they could use to kind of study matter, and a guy by the name of Tesla invented a device that made really high voltage electricity. When I get back to school, ask me to show you this, all right? And chemists were zapping everything, all right? They were zapping solids and liquids and gases. They were zapping everything with whatever with whatever high voltage electricity that they could find, all right? And they could make, right? They didn't have to find it. They had a device that would, make high voltage electricity. And as they worked with these Crookes tubes, they discovered that when you hooked electricity up to these electrodes here, right? So if I took my power supply and I hooked some electricity up to this thing here, some high voltage electricity, positive, negative, that type of thing, that there would be these particles coming out of this piece right here. Particles coming out here, all right? And it didn't matter what type of metal was in this position, right here, right there. They could switch out whatever metal they wanted. They could put copper in there, or they could put some gold in there, or they could put some, well, no, I'm just being silly, iron in there. You get the idea. And it didn't matter what type of element they had in there, and these particles would come shooting out. And these particles had certain properties. They were very small, they were very fast, they moved in straight lines, and they had mass, because they could knock things down, like this target here. They could make that fall over. So it wasn't light that they had discovered here, but tiny little particles. And it turns out that these little particles we now know are electrons, all right? Now, what does this have to do with the atom and Thomson? Well, scientists were naming these things. They were calling them electrons, little tiny pieces of electricity. That's what electron means, all right? And it was Thomson, all right? It was Thomson who decided, let's then think about where these electrons are coming from. And so he realized that they were coming from all of the atoms that made up those pieces of metal, that they were being ejected from the atoms. So he simply concluded that the atoms must be the origin of these little pieces called electrons, all right? So electrons were found and originated in the atom. So what's Thomson's big, contribution to the theory of the atom? It's that he put electrons in the atom. Scientists knew about these electrons. Using the new electricity, they were zapping things and discovered these little pieces of electricity. And Thomson simply said, well, where do these electrons come from? Well, they come from the atoms. Excuse me. Okay. His hypothesis stated that the electrons were embedded in a positively charged sphere. Okay? So we call this sometimes the plum pudding atom. This is an English representation. Thomson was English. And simply then we have these negatively charged electrons in this sphere of kind of gelatinous positiveness. all right? And it has to be kind of gelatinous, like jello, because if the electrons can be ripped out, then it means that they've got to be able to be like kind of sucked out of that jello and then sent along their way if you were to, say, use it in a Crookes tube, all right? So, I like to think of it more like, that jello salad that you see in Christmas when, it has the fruit floating in the middle of it. And you can think of the fruit pieces as being the electrons and the jello being the positive charge, all right? So that is Thomson right there. And he simply just put the electron into the atom. And again, another little video we're not going to do. Okay, the last guy we're going to talk about here, well, no, there is one more guy, is a guy by the name of Rutherford, all right? Ernest Rutherford did an important experiment using gold foil to analyze the inside of an atom. Now, this is usually a little animation that runs that explains the gold foil experiment. I'm going to just kind of show you the gold foil experiment, to draw it up here, because that animation isn't working. Okay, so here's what Rutherford did. Rutherford took a piece of rock that was radioactive and he encased it in a box. All right, so he put it in a box and he left a little opening right there at the beginning. Now, this particular stuff was, like I said, radioactive. Okay, so this is radioactive, and we're going to learn about radioactivity in a little later on when I get back. Anyway, radioactive elements eject little particles, all right? And this radioactive thing was ejecting what we call alpha particles, all right? Alpha particles, whoops, pardon the spelling. And an alpha particle is essentially a helium nucleus, all right? It's an helium nucleus. And it's relatively heavy, all right? Heavy, and it's fairly fast. It's heavy and fast. And scientists had discovered that certain elements, like uranium, all right, so this is probably uranium, eject these particles, and that's what radioactivity is. Rutherford realized that if he took these particles and aimed the particles at some atoms, he could get a sense for what's inside the atoms. Now, this thing is shooting off alpha particles in all directions, which is why he put it in a lead box. This box here would have been made of lead. It would have absorbed all these particles, and these would have come shooting out here, some alpha particles. Now, what did he shoot this at? Well, he shot it at a piece of gold foil. Now, gold is a great element to do this particular experiment with, AU, all right? And that's because you can hammer gold really thin. And he had very thin gold, approximately 400 atoms thick, all right? Which is not very much. 400 atoms is pretty small. And then what he did was he put a screen in behind this thing, all right? And my screen isn't going to be very good, but I'll put the screen around. He put the screen all the way around this stuff, a big screen here. And the screen was coated with a material called zinc sulfide. And what happens is when an alpha particle hits the zinc sulfide, so let's say we got an alpha particle, let's say it busts right on through, this thing glows, right? We'll make it yellow or something like this. This thing glows, woo, glows up. And that told Rutherford that the alpha particle made it through. So here's what Rutherford wanted to do. He wanted to fire these big, heavy, fast particles at this thin layer of atoms and see what they did. Now, if these atoms were made up of gelatinous goop, then we would expect most of the atoms to bust right through. They might encounter a little electron and might be, oh, well, another very important thing. Alpha particles are positively charged. They're positively charged, and that's very important. Because if an alpha particle encountered a little electron, it may have deflected a little bit, and it may have moved over here to the side a little bit, but not much. So the prediction was, if it was made of gelatinous goop, then that particle should just bust right on through. What Rutherford discovered was that, yes, most of the particles went straight through. But he also discovered some that bounced over here. We'll make a little light spot there, and maybe bounced over here. But the weirdest ones were ones that were way back here and way over here. So he discovered, or he determined, that some of the alpha particles were taking off that way, but some of them were coming right back. And those are the important ones right there. We'll put an exclamation mark right by there. We'll put a little mark here beside it to make it look important. All right, that's very important, because if you're shooting big, heavy objects at gelatinous goop, you would expect it to go straight through. But in actual fact, some of them came back. And that's very, very important. And I'll explain to you in a moment what that means. But it was these ones that came back that were the situation. Now, one last little thing I want to show you before we talk about what this means, and I can't advance my slides. What's going on with my program here? Here we go. This is a simulation that I sometimes run, and the simulation isn't going to work for me here because I'm not on my school computer. But this kind of shows what can happen here if we have our alpha particle. And here's what Rutherford believed was taking place. Here's what we now know as the nucleus of the atom. And those alpha particles that kind of started up here would have kind of zone along here and maybe would have been deflected a little bit, all right? Not much of a deflection. And these that were way over here would have hardly been deflected. But any alpha particle that got really close to the nucleus would have been deflected very strongly because of the repulsion of the two positive charges. So here, another one here would have been deflected very strongly. And if one maybe came straight on, oh, my line, it might be deflected right back, all right? So Rutherford knew his physics and laws of physics and knew that if you had a positive charge running into another small positive charge, you would get these deflections back and you would get these zinc sulfide to glow. You'd get a scintillation, it's called. So that explained why most went through and why some came back. The existence of a small, all right, heavy, positive, and he used the term nucleus, all right? A small, heavy, positive nucleus is what he had to predict. So that's the important thing that Rutherford determined. He determined the existence of the nucleus. It's fabulous. That's very important, the nucleus. So Rutherford's big, important thing is he put the nucleus in the atom. He believed it was positively charged because the alpha particles were being deflected away. He stated that the electrons could orbit anywhere around the nucleus. Actually, he didn't. He really wasn't concerned about the electrons, but he knew that they had to be moving, kind of like in a solar system. So he said, well, they've got to be moving out there somewhere, but there's problems having electrons whizzing around a nucleus. There was physical problems that had to be fixed, and he knew there were problems with this. But he did not have the solution, and the next guy we talk about in a few classes, Niels Bohr, came up with the solution for that. Later discovered that the positive charge was due to a proton, and Rutherford's atom is sometimes called the solar system atom. Oops. And that's because it has this big heavy piece in the middle, the nucleus, like the sun, and it's got things whizzing around it, the electrons, like the planets. Okay, one last guy to finish off here, to finish off all the particles that we need in our atom, and that is James Chadwick, and he conducted experiments which led to the identification of the neutron, which is a neutral particle located in the nucleus with the protons. This was done about in approximately 1930. Oops, that's not a 3. 1930, that's horrendous. And it took them a long time to discover the neutron, and that's because a neutron is neutral, and you really can't do much with a neutral object. You can't deflect it with a positive charge or deflect it with a negative charge. It doesn't make zinc sulfide glow like the alpha particles. So it took a while for them to discover. There's a great story on how that works, but you've listened to my voice enough. You don't want to hear anymore. Okay. So that brings us to the final little thing in today's lesson, and that is kind of an accounting of all of our particles. And the first particle that we kind of came along was, I guess, the electron. Let's save the electron for last. Let's start with the proton. Okay, proton, sometimes written as a P with a little plus. All right. Relative charge. It is positive. By the way, a plus with a VE is my short form for positive. Its location is found in the nucleus, all right? And its relative mass, and when we say relative mass, we're comparing it to other particles like the neutron and the electron, so its mass relative to something else, we have 1. And there is a unit to that. It's called 1U, and that U stands for an atomic mass unit, and we'll get to that a little later. The next particle, the neutron, and it's sometimes written as an N with a little 0 because it has no charge, and it is neutral, and it is found in the nucleus, and we know that, and its relative mass is 1, all right? And the last guy, which is actually the first guy we came across, the electron, and that has a E negative, and it is a negative charge, and it's important to know that the negative of the electron completely cancels out the positive of a proton. It's found in orbit, and its mass is approximately 1/2000th of a U. So it has a very small mass, all right? So its mass is much different than the proton, but its charge is exactly opposite to the proton, and it cancels it out. Okay, and that's where we are ending for today.